I'm Gabrielle Thériault. I'm marketing manager at Gentec-EO. And I won't be the one presenting, but I just want to introduce this presentation so that you know that to make sure that your laser system is efficient, you'll need to track its performance. And we want to provide you with information on how to use power measurement as a monitoring tool. So in this webinar, we will guide you through best practices for accurate and repeatable laser power measurement. And I'd now like to turn over the webinar to our physicist in charge of sales for USA and Canada, Félicien Legrand. And you've seen the titles. So I will be back at the end of this talk to help out with the Q&A session.
Thank you, Gabrielle. Pleasure to be there. I'm gonna start by sharing my screen to launch this presentation here. There you go. All right, how to monitor laser system performance with power measurement. Thank you very much for attending. It's a pleasure to be there. We have an hour together. Presentation will last for between 40-45 minutes maybe, and then we have some room for questions, and where you're more than welcome to interact with us to share about your laser application needs. What do you do with your lasers? How do you do it? And how can we help Gentec-EO as a company to achieve your goals? All right, let's jump into it. So first of all, who we are. Gentec-EO as a company, we have been providing laser beam diagnostic solutions since the 70s, providing beam profiling cameras, laser power energy meters, high power measurement solutions, both off the shelf, ready to go and customized for your very needs. We are ISO 17025 compliant, meaning that we do manufacture and calibrate our own devices. We are headquartered in Quebec City in Canada, with offices in the US and in Japan. All right, we pretty much cover all laser industries from consumer to medical, manufacturing, directed energy, and research. And just so you know, any standard Gentec-EO detector that we deliver is coming with a NIST traceable calibration. So the best calibration out there for you to benefit from the best accuracy. Okay, so measurement is key. Whether you're involved in designing a laser system, product development, safety compliance, quality control, productivity improvement, repair and maintenance, you always ask yourself the question: is my laser working like it should? How can I improve it? What can I do? What I need to do with my laser? And this is how laser power measurement comes handy. So the way we're gonna divide this presentation is the following. First of all, why do I need to measure my laser power? How my field of use and my industry or my research field will benefit from laser beam measurement and laser power measurement. Then what are the best tools to measure that? And then how to measure such power accurately. I'm gonna give you some tips and hints to use those devices to the best of their capability. First of all, why? Next, I'm gonna show you a quick video that I made. Okay, so bottom right, you're seeing a laser system that I bought online for, like, say, $100. Really simple. You find that online, delivered the next day, and this claims to be eye safe with a maximum output power of less than 5 milliwatts continuously. Now, there are 3 laser beams going out of this system: one blue, one green, and one red. Okay, so first of all, you can see that the wavelength entered there, showed there on this sticker. It shows the 650 nanometers and the 532 nanometers, which is the red and the green laser beam. Even there, the blue laser beam is not shown, is not identified. So first of all, why do I need to measure laser power? First of all, for safety. As you can see there, top right, I've measured like more than 50 milliwatts of laser power for something that claims to be less than 5 milliwatts eye safe. So first of all, that was a big problem. And then you can see bottom left, this measurement is more than 15 milliwatts. That's for the green laser beam. Top left, that's the beam profile. We can talk about that a little bit more later. But yeah, first of all, when you buy a system or when you manufacture a system, let's make sure this is eye safe for the people using it. Around the enclosure, if it's a high power laser, that you need to build an enclosure to make it safe. And then for some commercial laser system, please measure it and be sure this is safe. Was clearly not the case with that one. All right. So once again, why do I need to measure my laser power? We're gonna look through the eyes of three different kind of realities, from the R&D point of view, production point of view, and service. So first of all, if you're working in the R&D department and you need to design and come up with a way to build a laser, there are a couple of things that you need to take in consideration. For example, you have laser source, you can add optics and lenses to collimate your beam and to work on a given output in your environment where the laser beam gonna hit, and the matter light interaction will happen. So first, you'll need to design those things, and you may be involved in the in designing and defining how it has to be assembled in production. You need to define, for example, the steps for your colleagues in production to build this very system. Then there are a couple of things that could go wrong or not as expected. For example, the laser source will age, could malfunction. You can see some ramping up sequences in the power output. You can see some thermal lensing effect as well that you need to take in consideration. And power measurement will be a really helpful, one of the main tools that you need to use to qualify that, to quantify exactly this behavior. The optics and the lenses, they could get dirty, damaged, misaligned in the environment, will play a key role with vibrations, air drafts, dust, light, temperature, humidity fluctuations. So all of that needs to be taken into account when you want to build a laser system and build specifications that you could use for your research or sell to your customers. So then, a couple of things to keep in mind when you design a laser system. Keep in mind, first of all, that you will need to validate a design in your specification. So on your optical table, in your optical bench, having those tools available in a neat way, in a clean and accessible way will be really important. Then you want to understand your system dynamics. For example, if you plan for your thermal effects to imply some thermal lenses effects, some ramping up sequences, or some shift in the focal point position, for example, this all has to be quantified and power measurement will come handy. Then let's say your manufacturing system for medical use, then you need to certify for safety. You need to comply with the standards that applies, for example, FDA standards, or what you need to use. But then once again, it's really important to be sure the system is safe. And as well to plan for checkpoints in maintenance. When you sell a system to a customer that you have it working in the field, you will want your customer to be sure that after 6 months, a year, 5 years of operation, you will provide them the tools to verify if the laser system is operating as it should. There are high chances that the environment will play a role in making the laser output different. For example, in having some lenses affected by the environment and some dust, for example, or some condition that are taking place in the plant. So whether you design from the very early stages to provide a power meter inside of your machine, or to let the customer have the possibility to make the measurement themselves, you'll need to think about that when you design a system. Okay, so then what kind of measurement I can do? What I call direct or indirect measurements are two possibilities. First of all, I call that a more invasive kind of measurement. It's a direct laser power measurement at a given time. You take 100% of your laser power, basically you block your laser beam before the delivery point for what your customer needs to do. And so you take a power meter that's adapted to this laser power, of course, you watch out for damage thresholds, be sure that the detector is adapted and that it won't be damaged from this laser beam. But then you have your production and your process, your research that is stopped because you're making a measurement. You file out a report, for example, and then you get back to production. The non-invasive way to do this could be to use an optical peak-off of the laser beam power from a beam splitter or reflection off of surface, for example. So you can use a fraction of the incoming laser power. That will allow for real-time monitoring. So that's good. You do not have to block your process 100%. And that could require a smaller detector. A typical optical peak-off from a semi-transparent mirror could be between 4 to 10%, for example, transmission. So that will require a detector that's less capable than taking the 100% of the laser power. So a smaller qualified detector could be used for the non-invasive way to measure this, and which is more and more used. because you don't want to stop all your processes. And that could be nice to measure the laser power simultaneously to how your laser beam is processing your parts or your sample, or whatever you need to process. So you can see both things in parallel. Okay, then decide from a spot check measurement or a continuous measurement. Depends on what you need to do. First of all, the spot check is what we call a single shot power measurement, typically during 5 seconds. During 5 seconds, a measurement like we are offering with our Pronto series power meters, you just take a snapshot of the laser power. The detector will block the beam temporarily, yeah, but that's for a short period of time. And then you can go to different places along your beam path to measure the attenuation of various components and see how your laser beams behaves along this propagation axis. Then for continuous measurement, for example, if you're doing burning station, aging testing, there you will want to measure your laser power for a longer period of times. Or if you want to monitor how the ramping up sequence is doing, any shift in the power level and these kind of things that you want to measure all the time, of course, it's good to use a permanent dedicated detector that's placed in front of your laser beam, and that will measure that. And if it's permanent, it could go well in parallel to the optical peak-off solution. You take optical peak-off, split your beam in 2 parts, and have one detector that's continuously measuring your laser power. All right. Now, more on the production point of view. So we've discussed how to design a system, what to keep in mind when you design such laser systems, and then from production point of view, when you use a laser system. I'm going to show you an example that I've prepared a video for another audience. I've been running some laser wood engraving kind of projects, and I'm going to show you a video where I was using a laser power, a laser system that was rated up to 3 watts, and the power was decreasing over time. I'm going to show you the video and get back to you shortly. All right, let me see if you can hear this sound. Okay, I gotta.
Diode rated. Okay, right. So this is a blue laser diode rated for a maximum of 3 watts of optical power. When I received it back in November 2020, it provided a maximum of 1.8 watts. Now shows max 1.11 watts. I'm using this Gentec-EO laser power meter connected to my phone. Really convenient to use to provide a calibrated measurement of the laser optical power. So basically, for a given laser power, it tells you how to set your CNC scanning speed to get consistent engraving results for your needs.
All right, so long story short here, I was engraving wood, but the power required to get a consistent engraving, so the power should be the same, but the power of my laser was just decreasing over time, months after months. So to get the same amount of energy absorbed by my piece of wood and have the engraving resolution that I wanted, I just needed to slow down my CNC speed to get the same amount of energy absorbed by the material for a decreasing laser power. So that's exactly the point. That could happen for laser wood engraving, welding, cutting metal, welding, and any kind of process that takes some time. And if you have a laser power that's decreasing, you need to adjust the speed of the process. So you want to monitor that and be sure to have consistent results in the end. So that's exactly it. Power level progressively getting lower over time. You can get some power level fluctuations unpredictably. It could be an issue as well. It was not my case in my application, but that can happen. And a sudden drop of power as well from misaligning optics, cavity that's heating up too much, these kind of things that can affect your output. And all of this will result in the end in a loss of productivity. Some examples here: weld failures, incomplete cutting, and incompleted surface treatment, longer processing time, wasted materials, downtime for maintenance and repair, and worst of all is the lack of confidence in the technology. If you're not able to use a reliable laser tool, what's the strategy? You want your laser to behave as expected, and if it's not behaving as expected, at least quantify the difference in behavior and file that and take appropriate actions. Okay, so what is to keep in mind? So monitoring laser power, it's kind of clear that it saves cost, okay? But when you're operating those lasers, it's good to keep in mind safety and compliance first. When you're running for example, medical lasers in the field, you need to come up with a plan to test those lasers regularly, and to be compliant with the standards that you need to use, to have, and to be safe. So process control, for example, we have customers running additive manufacturing machines, and before any batch of processing, they measure the laser power to be sure it's consistent, to be sure it will take the quantify the same amount of time that they can expect between batches of production, between the parts that will be added to this metal sample in this case. And then an example of a feedback control loop. That's something that is more and more implemented at our customers running operations in the manufacturing field. Let me give you some more details on that one. So that was used in the automotive industry. That was a welding station used to weld a number of parts per day with a number of shifts per day. And the laser power was checked twice during each shift of production. Basically, how it works with the following: they just took a 30-second measurement of the laser beam power with a water-cooled detector that allows for a long period of time of measurement, and then they were replicating exactly the time it takes to process the part. It was 30 seconds because they wanted to monitor exactly how the laser power is ramping up, then making a plateau, and then maybe falling down. And then if the maximum power, the average power, what they wanted to measure was different than the power that was expected for the process, if the difference was larger than 100 watts in this case, so the test failed, and all alarms were set and people were informed. So for technicians and engineers to get in the production line and take appropriate action for using another laser, changing parts, and they had their strategy for that. But most of the time, the test was passed, and the laser was able to get back to production. So yeah, so the key here was the consistency in the number of measurements per day, for example, just before any given shifts of production. So that was some examples for production point of view. Now for service. So let's say you do not try to exactly improve your process, or you've done that. Process is optimized, that works well, but you'll know that your laser will age. Some parts will have to be changed, and you need to have a maintenance plan. And that both applies for research applications in the lab and used in the field for manufacturing or more industrial kind of application. You want to be sure your laser is consistent. So then a quick video here. So that's the output length of a welder system that is used for welding metals. So facing downwards to a power meter there, which is a Pronto 250. Just pressing play, and the detector will wait for a beam to heat up the surface of the detector. Once that is done, it's counting 5, 4, 3, 2, 1, 0, and displaying the average power of this laser, about 26, 27 watts continuous. So here, I'm going to stop the video quickly. So the application there was just cutting through metal to this piece of metal that was turning silver here. So initially, the laser a couple of years ago at this customer was providing more than 60 watts average. It's a pulse laser, right? But to get the results that they wanted, they needed an average power in the range of 60 watt. The repetition rate was around 80 kilohertz on that one. But by monitoring the laser power consistently and weeks after weeks, months after months, they saw a decrease because of the environment that was kind of dirty, and because of the lenses that were slightly to clean up as well. So they're here to get a consistent result in this cutting. It took simply more loops and more batching and more time of processing for a given laser power. That was 27.2 watts, and it was taking twice as long as it was needed when the power was double that. So another example, and you've seen this tool, which is really convenient. Just place that in front of the laser beam, press play, and your measurement is done in a couple of seconds, and you can just monitor how your laser is behaving. All right. Okay, quick reminders, what can go wrong? Once again, aging parts, and most importantly, I think sometimes just accessing the beam and where you want to make those measurements and to replicate what the material is seeing could be difficult. For example, if the system has not been designed with measurement in mind from day one, perhaps it's just impossible to get there and to place such power meter at this place. So that has to be thought of when you acquire, when you install a laser system. And then you need to train your workforce and to deploy and to come up with a recalibration strategy, for example, both for the laser system, have it measured, and for the measurement tool itself. Because the measurement tool for high-powered application like this is mostly based on thermal pile detectors, thermal effects. So that again has to be recalibrated. We usually recommend to get such detectors recalibrated on a yearly basis, but that depends on your application. And since we all know with COVID-related restrictions that traveling is more tricky than ever, so come up with the right strategy to send people on site if needed is really important. Okay, so for service, we'll need to prepare, and you guys need to be sure what is most relevant for your reality. For example, keep track of those things. How many different laser stations we operate? How many different laser models? Do I need a given detector that's different from one laser model to another, or can I use one detector for all? This kind of questions. And when were they installed? Typically for my application running 24/7 operation, do I expect the system to need maintenance after 3 months, 6 months? Let's measure and we'll see. What about third-party maintenance? Once again, traveling is tricky. What do we do? Do we send our own workforce? Do we rely on third-party companies that can get on site? And how do we manage employee training? How do we manage laser safety? Do I need to hire a laser safety officer? Is that justified? Is the expense is justified for my needs? And how do I manage on-site access? All those questions. Okay, so I think we kind of understood why this is important to measure the laser power and or beam size as well. If what matters for your application is to measure power density, then measuring the beam size is important as well. We have tools for that also. But then let's focus on power measurement. What are the best tools for measuring that? So before answering this question, there are the key questions to ask yourself, and we're here to help to make the process straightforward and simple in the answers. Of course, first of all, what is the laser wavelength? Once you know that, ask yourself what is the minimum and maximum expected power from your design, from the optical component you might had in the between the source and the sample. What is the min max expected power? What is the expected beam size and profile as well at the measurement point? If the laser is pulse, you will need to know what is the minimum maximum expected energy per pulse, repetition rate, and pulse width. If you do not know about this at all, you can take a more capable kind of detector to just get a range of those quantities, and then refine the selection to something that is more accurate. And we're here to help in that in those developments. Then, for how long do you need to measure your laser power? Once again, is that just a single shot power? Just okay, I'm 25 watts for 5 seconds. That's all I need to know. Okay, I'm 4.5 kilowatts, and I just wanted to be sure I'm at the right range. And you want to measure that for a couple of seconds, or do you want to see a drift in power and you want to measure for hours, for days, or for months, for developing new sources, for example? And then, what kind of integration do you like? Do you want? Is that something you want to be a detector to be plugged to a computer, to a smartphone wirelessly? Do you want to use a PLC in your industry and to run some automation on it? Do you want to use Ethernet and probe the detector once in a while and get some measurements? It's all available, and it all has to be qualified for your reality. And then a timeline and budget to get this implemented. Okay, so once you know the answer of those questions, you could use such tool online to answer the answers. That's a tool we provide at the Gentec-EO.com. And once you've entered your expected specifications or kind of parameters you want your laser to provide, then we offer a selection of detectors, and we offer the knowledge to refine the selection to your exact needs. Some examples here of detectors, some examples as well of the different absorbers that we integrate in our solutions. We offer the highest gamma threshold in laser power density on the market, and laser power and laser energy density as well. Thanks to those absorbers here, we provide up to 100 kilowatt per square centimeter in laser power density, and up to 300 joules per square centimeter in laser energy density. So And more on that, feel free to ask a question. I'd be happy to help. Some examples here on what we offer is pretty simple. Standalone display if you want to get rid of connected devices that can do the measurement without being connected. PC connected, wireless. We have some several options. Presentation here. What kind of technology is available for typically measure laser power? From the picowatt level, we mainly use photodiode, really sensitive photodiodes, as well providing NIST traceable measurement. Then going to the milliwatt, to the hundreds of watts, and up to the 2.5 kilowatt range, we use thermopile detectors. And then above in the kilowatt range up to hundreds of kilowatts, we use water colorimeters, where they're measuring a difference in temperature between the in and outlet, and water flow rate will be derived to provide the laser incoming power. Okay, so here I'm going to show you an example of measuring a laser beam power that was rated. This is a laser we're using in a calibration lab that goes up to 5 kilowatt. So then I'm going to show you a couple of tools here. First of all, we have a beam expander. So on the left hand side, that is used to simply enlarge the laser beam size to be sure we comply with damage threshold and to be sure we have repeatable measurement using these absorbers. And you'll see that some a good guideline is to use between 50 to 70% of the surface of the absorber. It could be smaller than that, thanks to the high damage threshold, but it's a good habit for a good repeatability. So first detector that we have in beam path after the expander is a Pronto 10K. This one takes up to 10,000 watts, but for 5 second max. The same kind of technology I showed you earlier with the welder. So let me show you how we set this device. So simply press play on the monitor that you see on the top right corner, bottom right corner, sorry. So it will wait for the beam to heat up the surface. So it's kind of a really powerful laser, so we get the hell out of it and we turn on the laser when it's safe to do it. You will see some back reflection. Camera is capturing some purplish colors. So then after 5 seconds, what you see is a 3.88 kilowatt measurement. It's traceable. Plus minus 5% accuracy, absolute measurement. So that was done during 5 second quick check. But let's say you'd like to measure this kind of power, but for a longer period of time to see how your laser is behaving, then we're going to remove the first detector and let the other one take over, the one that's water cooled, so they can take for whatever period of time we want to measure. So I've sped up the speed of this, I've accelerated the speed of this video here 4 times just to get faster to the stabilized output. And we'll see this, the Maestro, the monitor, the display here will go to 3.85 kilowatt, which is so consistent with the other measurement, because you can apply a plus minus 5% absolute accuracy to this calibration uncertainty to this measurement. So the two measurements here are consistent, and you can run this HP product, the one that is water cooled, once again for hours, for days. All right. So then, okay, some tricks and how to measure the power accurately. What are the best ways to use such tools and those devices? So first of all, let's make sure that we use a detector that's within specification. So that's where we're here to help. To select the right tool, even if you already have those tools in your lab. Should I use this kind of pyroelectric detector and make, I don't know, pulse-to-pulse energy measurement for pulse lasers and just multiply that by the repetition rate to get an average power measurement? Should I use a thermopile? Should I use a calorimeter? So we're here to help, and be sure to use those detectors within the specs. Then you can start your laser to make it stable, in a sense that you will have in thermal equilibrium with this environment. Depends on the kind of technology, whether it's fiber or diodes. That could be kind of different, but 20 minutes typical. Then set the wavelength in the display that you're using. Then use once again a beam size at between 50 to 70% of the optical aperture is possible, whether you're using the natural divergence of the beam or using an expander. Then center the laser on the detector. That will help for repeatability. And then for thermal detectors, not for photodiodes, or let's say we're focusing more on high power applications here. For thermal detectors, have the laser on, heat up the surface, heat up the detector itself for as well having it in thermal equilibrium. So you have the full system that's stable. Try to limit the air flows around and air circulations. Then block your laser beam. So for high power laser, that could be tricky. You cannot block it like with a small card that you can do for ISF lasers. I've seen applications where you could use beam dumps that could be placed in the optical path. So turning down turning off the laser beam. If you want the laser to be still functioning, you can use a beam dump and to dump the energy, and then having the meter that's used for calibrated measurement. You can do the 0 on that one, and then removing the beam dump and have the 100% laser power going to the power detector. So zeroing the meter is to subtract the background to be sure if there is any heat sources or any the reading that is not at 0 exactly. You can just remove this background, and then with your laser back on, you could use an averaging method, for example, to smooth out the reading of the laser power. All right. Some tips. It's really important for thermal detectors to have a stable environment in terms of heat fluctuations. Otherwise, for low power stuff, you could use a photodiode that is more flexible for these things. Deactivate anticipation. Anticipation is a feature that we provide with our detectors. It's a software-based feature. Basically, we will look at the increase in power using a thermopile detector, a thermal detector. The reading is not stabilized instantaneously. It will take some time for the energy to be absorbed by the absorber and transferred to the thermocouples or the water if it's a calorimeter. That takes some time. So basically, you have ramping up an increase in power, and the software will look at this increase to derive an output stabilized measurement. So knowing the physics of the thermopile, it will know if I'm seeing this kind of increase in temperature, I know that the power will stabilize at this level. There is an added uncertainty to this process. So if you want something that is more accurate, it will take some more time. You can deactivate the anticipation feature. Use averaging. It's a bit longer as well, but if you want a stable measurement. And set your measurement range before letting the display do the auto scale. You kind of know, am I expecting, I don't know, 100 watts, 150, or 800 watts? You can just set the range, the accurate range in your measurement device to save some time. All right, so I'm going to show you some an example here using a low power photodiode detector and a diode source here. So how to set a display, the monitor here that is on the corner top right. So first of all, so I can control the current driver, the current that's going to this diode to control its output power, measured by the photodiode that's here, that's connected to the display there. So the first step to do is to tell the device here. So okay, so that's an optical chopper that I'm using here, but I won't using this demonstration. I'm gonna skip this and go to how I'm gonna set my display. Yeah, first I need to tell the device which mode I'm gonna use. I want to measure power, and I'm gonna check this box, the attenuator box, because I'm using an ND1 filter on this photodiode there. So I simply need to tell the device to multiply the signal by 10. Then select the wavelength, the 659 nanometers red laser diodes. I'm going to tell the device the wavelength to get a calibrated measurement. Then select my range. Do not expect more than 3 watts, 3 milliwatts, I'm sorry, of optical power with this low power diode. So during doing so, when I'm gonna zero the meter, it will just zero the meter on the range I've selected, 3 milliwatts. So that will be faster. So then I'm controlling my laser output power and going to 136 milliwatts roughly. Next step will be to tell the device that I have an optical splitter here. That's a microscope blade that I was using for splitting the beam. And then here, I'm gonna stop it quickly. So the splitter there, allowing me to split my beam in 2 parts, one going to the detector and another one going to photovoltaic cells that I use for my application that was transmitting audio signal through a laser beam. And then so and I know the attenuation of this glass piece here is about I've measured 17%. So I need to tell my display that I need to multiply my reading by 1.17 to get back to the actual incoming laser power that the diode is providing. So then one thing that's missing is to zero the meter. And gonna do that by next step. All right, go maximum power. Okay, so I'm gonna press the 0 button here on, but before I'm gonna block my beam. This is low power, so with the card. So on, that would 0, get the rating around nanowatts. That's just background noise here. And then removing the card and getting back to my actual calibrated laser power measurement, which is 1.54 maximum laser output power that this diode can provide. And I had another tool that I use, which is the Pronto SI, which is the handheld. Oh yeah, I'm sorry here. So that's just the optical chopper that has a 10% duty cycle. So you see when it's on, power reading is decreasing, but it's not the point here. So here the Pronto SI handheld laser power meter up to 800 milliwatts. So I'm going to use it to place it in the beam path and to see if I have a consistent measurement. So selecting the wavelength again, 659 nanometers, and then placing the photodiode 1 centimeter square area there in the beam path. And then do I see, hope you guys can see it because I have my ribbon on top of my Zoom window, but it's showing 1.54 as well milliwatts. So that's consistent. It's a really handy tool to scan around an enclosure, be sure it's safe and for low power application. Okay, that kind of concludes the presentation. Feel free to jump online, go to our website. We have plenty of resources, application notes, blog article to be sure to use those devices. And any questions, I'll be more than happy to help. I'm gonna stop sharing the screen and get to the chat function there.
Hi. Okay, so I've been monitoring the chat and Q&A. There's one, maybe we'll start with that one directly in the chat. So it was, in the case of fiber lasers, what is the role of temperature and humidity of the working place? And what are the allowed fluctuations in temperature and humidity? Could you comment on that?
Yeah, that's a really interesting questions. In terms of the technology itself, fiber, diode, a different kind of laser technology, I need to tell at Gentec-EO, we are more the experts in measuring the output of the sources than to design those sources. Those sources are made by our customers and our partners. But what we've seen in terms of temperature and humidity impact, that is an excellent question. And we could use the cases that we've done in the past with our customers to answer that, but I don't have an answer on top of my head for this. But surely, if you want to monitor what is the impact of humidity and temperature, there is no other way than measure the output power or beam size, for example. If you expect that for whatever reason you can have some thermal lenses effect that could affect the focal point area and the region where the focus is made, measuring it with a calibrated tool would be our recommendation for sure. Yeah. But let's share about your application if it's something that you've been dealing with for some time. Yeah.
Yeah, I know that fiber lasers have been known to be much more stable than gas lasers, for example. So maybe it won't be much of an issue for them. We'll see. We've also had a few questions that kind of overlap, talking about how to fill the aperture and what are the best beam diameters to aim for. So let me just read one out completely. So how much inaccuracy can I expect if I measure power or energy with a laser beam having a diameter of only 5% of the available clear aperture of the measurement device? How much of the detector area is it ideal to use for a correct measurement? And how do you make sure that you're not clipping the infrared beam when demagnifying it for the purposes of covering the whole area of the detector?
Yeah, excellent questions. So first of all, when we recommend to use 50% to 70% of the surface of the absorber, that is for two things: safety, to be sure we are away from data thresholds, and repeatability, because you have a variation. I think that's a plus minus 2% linearity with beam position, typically in medium power application around 500 watts. So if your beam is not properly aligned, you will have a shift in measurement. You could have an added uncertainty. So when the beam is larger, first of all, it's easier to align. And when the beam is smaller, if it's well centered on the surface of the detector, it's pretty safe to say, if you comply with damage threshold and you're not cutting or damaging your detector, it's pretty safe to say that you can apply the plus minus 2.5% accuracy that comes with the NIST calibration. So it's a matter of having it very well centered, and it's a matter of respecting the damage threshold as well. And in terms of not clipping the beam, it depends. If it's a flat top beam, it's more simple to align and to not clip, because you know where the edges are. If it's a Gaussian beam, when you have tails of the Gaussian shape, that's why the recommendation of the 70% max. So if you comply with the 1/8 square diameter, that's fulfilling 70% of the surface of the absorber. So you have room for the tail of the Gaussian tails. You have room for the external part of the beam, and that will not be clipped.
Yeah, so the next question was, could you please explain why it's important to fill the aperture of the sensor? But you just
safety and the repeatability.
And what is the impact of poor laser beam pointing stability? Like, for example, fast-moving beam around the center of the aperture of the thermopile detector.
So that depends on how fast. If it's so, I've used application where you've seen my example where the beam is rotating on this piece of silver. So if you make this wobbling movement small enough to fit within the size of the aperture, if it's fast enough, this kind of thermopile detector, they have a typical 10-second rise time, response time. If it's fast enough, it won't tell the difference, whether it's a beam that's rotating or just a beam that's large enough. So the impact could be really limited. Depends on how fast it is, the energy levels, and if it's pulse or CW, for example. If it's pulse, you'll have to take into account the damage threshold in laser power density, so peak power density as well of the things. But usually I've seen application where it was really repeatable to use slightly shaking beams, and that was okay.
Okay, and
let me just add something, Gabriel, sorry. It depends on one thing as well, whether you're interested in making absolute measurement, that is according to the definition of the watt as the institutes are providing, for example, NIST or NRC. If that's your goal for research, I want to know I have 2.5 watts plus minus 2.5%, and I need to know this is not 2.6, 2.5. That's one thing. If you're more interested in relative measurement from one day to another, yeah, maybe the absolute measurement is 2.5 watts, but I measure 2.9 for whatever reason, but this is consistent. I do have 2.1 watts, but this is the same from one day to another. That could be what's relevant for your application. It depends what you need to monitor exactly.
Another one of our participants asks, which kind of cooling systems does one need for high power measurement?
So let's take a typical application in the, depends on the high power, but if we take let's say 12 kilowatt kind of welding or cutting applications, the detector we provide for that, I think we're running in around the 15 liter per minute kind of water flow, and the temperature range needs to be between 15 to 25 degrees Celsius. So around 20 degrees Celsius for the water temperature, and around 15 liter per minute for the flow rate. That's typical typical system, and that comes commercially available from companies providing chillers and water circulators. This is really this is not a complex selection there.
And is it necessarily always water cooled?
Nope.
High power?
It depends. That goes with the need of running continuous measurement. If it's continuous for a minute or more than a minute, usually this is water cooled. Depends, but if typically less than a minute, you could use detectors without active cooling. Could be fan cooled, or we could use the single shot power mode that we've been discussing, just for 5 second snapshot. Just we do see a commercially available system up to 10 kilowatt there, the one I've showed. So shown. So this one does not require active cooling. You just go up to 10 kilowatts and you get a calibrated measurement, but for 5 seconds. Otherwise, you can multiply those measurements. I think at 10 kilowatt you can make one measurement per 30 seconds. It needs to be verified. Every 30 seconds you can make a 10 kilowatt measurement. But then if a detector gets too hot, it will tell you, the display will tell you, wait a little bit and get it cooled down a little bit.
Oh, so many questions just came in. Sifting through them. Okay, about calibration, you were talking about some calibration factors, and we have also another question that was saying, how is a high power or high energy power meter calibrated before the first measurement when it's built? How do you get around to this
Good.
determining this calibration factors?
Sounds good. So this is wavelength dependent. First of all, the absorption of the detector itself. So what we do, we basically buy standards, gold standards from NIST, the National Institute of Standards and Technology in the US. We buy those standards and they provide plus minus 1% absolute accuracy or less than that. So we use those standards and we spend a fair amount of money to get them recalibrated on a regular basis. So we use those gold standards on one side in our labs. We shoot a calibrated laser beam, so a traceable laser beam to those detectors. We see the response of the gold standard, and then we shoot the exact same laser beam with a splitter actually, going to the detector that we provide, that we sell to our customers, and we adjust its response to match the rating of the standard, of the gold standard. And what we do on top of that, we use a spectrophotometer to measure the absorption of the detector that we provide, depending on the wavelength. And we enter the absorption coefficient inside of the PCBs that we integrate with our devices, with our detectors. So once you plug a detector to such a display there, shown there, first of all, you need to enter the wavelength. So the display will retrieve the calibration factor, the absorption value for this given wavelength, and apply this multiplication factor to the measurement, to the signal provided by the detector. And this coefficient of absorption was measured using those standards from NIST in the calibration lab. We have plenty of information on that on the website, and we can guide you to those resources to explain exactly how it works.
Thank you. And another one is, did I hear correctly that you recommend to send the detector for recalibration about once a year? How can you tell if it's a good time for a recalibration?
Excellent question. It depends on the application. I know that sounds general and easy, but we set 1 year as a general guideline. For example, if it's your first experience with a power meter and you don't know, do I have any drift in measurement? Should I get it recalibrated? Make the exercise to send it back to us after 1 year of use. So we'll make a first step. First step is we measure the response of the detector as received, and then we recalibrate it using our standards, and we see the difference. And then it's a partnership. We'll tell you guys, actually, your drift in power measurement is very small, or it's important. So after 1 year, for example, if we don't see any drift in measurement, let's try 2 years then, depending on your application. You go step by step. But if we see a large drift in measurement between the moment we make you've received it and the moment we receive it back for recalibration, then you need to come up with the right strategy. Maybe your environment is affecting the detector. Maybe it's not the right detector for the use. And I'm not taking repairs. For example, if you shoot a small laser beam every time and you get to the surface of the absorber discolorated, and you have some discoloration, but it's not necessarily damaged, but that could affect the measurement. First of all, if you see some discoloration on the surface of your probe, means that there's something to do, whether it's some repair or recalibration or use large beams. But then we will tell you after 1 year, the first 1 year of use, depending on how the detector is providing the signal, whether you should have it recalibrated shorter than that, every 6 months, for example, or longer. Typically, we see longer than that, because when we qualify the detectors properly, with the help of our resources, if you use it properly, it's not necessary to go that often. But that depends. If you're manufacturing medical devices and you need to comply with FDA standards, every year will be the rule. And even if your detector is behaving perfectly and you don't see any shift in measurement, you'll have to comply with those standards. So you need to ship it back for recall. But depends on what your lasers.
Okay, next question. If we use a laser to set the equilibrium, is there any concern when zeroing the meter that we will not be able to account for a portion of the power? Like, for example, if we're running 200 watts for 1 to 2 minutes, turn off the laser, zero the meter with the display at 50 watts. since the meter is restabilizing without the laser, wouldn't we only read 150 watts, which would be inaccurate in that case?
Not sure I understand, but if so that
what I get from this question is to make sure when you're doing the zeroing part, if you do the zero too close right after you've blocked your laser, is that going to affect the zeroing?
Okay, I see. Yeah. So it's good in any case to let the detector stabilize. So if it's a photodiode, low power stuff, that's really quick. The answer is the rise time is around 200 milliseconds, I guess. But for the thermopiles, it's just usually 10 seconds. So when you turn on your laser beam or you block your laser beam, wait a little bit. Wait for the signal to get stabilized, so the reading to be stable, and then you do the zero. So you're sure you don't have any ongoing effects or effects that are still going on or that are not stabilized that could affect your zero. So once it's stable, do the zero and then fire up back your laser and make your measurement. It's the same, goes in both ways. When you turn down your laser, turn off your laser, it will take some time to decrease the signal. And when you turn your laser back on, it will take some time, typically 10 seconds. If you use the anticipation feature, that will be far faster than that, but you could get some more fluctuation because it's an approximation. So yeah, taking the time. Yep.
Good. Now, if you're measuring pulse lasers, are there any things you should watch out for compared to continuous wave lasers? If what you want to measure is the average power.
Okay. So if you have pulse lasers, you can measure two things. So three things. First could be beam profile, that's one thing. Second could be pulse-to-pulse energy. So each given laser pulses will provide an amount of energy in joules, and you can measure that using pyroelectric detectors, not the thermopile detectors. The thermopile detectors we've been talking about during this webinar, they measure an amount of heat, basically. When the amount of heat in watts is larger, and the answer of the response of the detector is larger. With pyroelectric devices, you measure an increase of heat, so the variation of heat in the coming from the signal. So it measures pulse-to-pulse energy in joules. So if you know the repetition rate, when you measure pulse-to-pulse stability, you will know your repetition rate in hertz. You measure your average energy level per pulse by the repetition rate, and you get the calculation of the average power. So that could be a way to do this. But if you're not interested in pulse-to-pulse energy measurement, you just want to see the average power in watts, you could use a thermopile, the same kind of technology we've been discussing for pulse lasers. You just need to comply with power density damage threshold and power energy damage threshold. So paying attention to the amount of watts per centimeter square and joule per centimeter square. But yeah, thermopiles, they're useful for pulse lasers as well. Yep.
Good. We also have a question about high vacuum conditions. So
okay.
Are there any power meter heads that exist that would be suitable for very high vacuum conditions, like 10 to the minus 6 millibars?
Good. Yes, indeed. So we need to go through the specs exactly, but rule of thumb, if you take a thermopile detector, the off-the-shelf as we can sell, we have the possibility to make them vacuum ready by changing some properties. I cannot go into much details here because there is confidentiality, but yeah, we can remove some components or alter some other components to really limit the outgassing and make it stable and ready to go for 10 to the minus. I have 10 to minus 7 torr in mind, but I think that will work for the vacuum level dimension. So high vacuum applications, they are covered. Yeah.
And then we don't find them off the shelf. It would be a custom.
It's customized, cost effectively done, and we do provide those detectors on a regular basis to our customers. It's not shown on the website because it really depends on your setup as well, and especially in terms of the connectors, the flanges, and what kind of connector you need from inside the chamber to the flange, and then outside how you want to retrieve the signal. So we usually build that on a custom base. Yeah.
I think we still have time for a few.
Yeah, go ahead.
Also from the chat, does the change in room temperature affect the temperature, the detector performance for the case of pyroelectric detectors? Say an increase in room temperature from 22 degrees to 26 degrees.
It's not expected to be that important because a pyroelectric detector, once again, will sense the variation of heat brought by the laser beam. So if your room temperature will change, it is not expected to impact the measurement accuracy significantly. From 22 to 26 with a pyroelectric detector, you should be safe. Yeah. And yeah.
Oh, I just lost my window here. Q&A. Some more just came in. If I'm using a pyro sensor to measure the pulse energy, but my laser emits pulses at 1 kilohertz with relatively high CW background.
Okay.
Let's say background is 20% total power.
Okay.
What energy will a pyro sensor actually show?
Good question. With a 20% CW background, I'll need to verify on that one to be sure, not saying anything stupid. But I think one way. So to be sure about this 20% background, one way to measure it could be to use a thermobile. But with a pyroelectric sensor, since it's sensitive to pulses, that should be not too much affected. But on that, with the CW background, I'd like to verify that to be sure. And I'm sure we'll have the coordinates of the person asking you.
Yeah, I think we have the contact information, so you'll get back to that person directly.
Yeah, sure.
I think we're almost done with the time. Do we have time for another one? Okay, well, that could be maybe a good one too. So the damage of the detector is defined, the damage threshold, by the intensity with the maximum given in kilowatts per centimeter squared. So what is a typical number for peak intensity? So in this example, the person is using ultra short femtosecond pulses. So the peak intensity goes to gigawatts per centimeter squares easily.
So there quickly, we need to rely on the power density. The energy density Damat threshold. We need to get back to joules per centimeter square. And we do provide those energy density Damat threshold given the pulse width. So if you know your energy level, you divide by the pulse width, you get the peak power. So we do not provide peak power density Damat threshold. We provide energy Damat thresholds, so energy density Damat thresholds, but for given pulse width. So that goes in parallel. So I don't have all the numbers in mind, but typically with the ubiquity latest release that we do, we go up to, for long pulse width, I'm talking milliseconds there, I think we go up to 300 joules per square centimeter, and I think we go up to 8 joules per centimeter square for nanosecond pulse width. And the rule of thumb is to use this Damat threshold and kind of divide it by 10 when you go from nano to pico, and divide it by 10 again when you go to pico to femto. So maybe roughly 0.08 joule per square centimeter for a femtosecond laser at the threshold, to be verified, depending on the wavelength, depending on the repetition rate, depending on the average power and everything. But we do have these quantities available. Yeah.
Thank you. I think that's maybe you have a final word to wrap up.
Well, I'm really curious to hear about the real world applications there, and to answer needs that will come up. Yeah.